between combinations and permutations is whether or not the order matters, and in combination questions, the order doesn't matter. So we're going to look at what kind of questions deal with that idea. We saw the formula already. Actually, it's a small typo here. There shouldn't be a line there. But we're mainly going to use NCR as our notation. And all a combination is a permutation with the order taken out. So when you take a permutation and you divide by R factorial, what you are basically doing is dividing out the order. So if I have AP5, that's like 5 spaces, 1, 2, 3, 4, 5, where the order matters. 8, 7, 6, 5, 4. If I then divide this by 5 factorial, then all of the ones that have the same numbers in different order would all get taken out, and your 5, no matter what the order, would be considered the same. Combinations, we use the formula a lot, and we saw that sometimes there's combinations that are the same. 10 choose 6 is equal to 10 choose 4. Easy to see from the formula, but also easy to think about if you have 10 people and you're going to make a group of 4. How big is the other group? 6. The order doesn't matter. Every time you make a group of 4, you automatically also make a group of 6. So making groups of 6 is the same as making groups of 4. And we can get into things like playing poker. If there are 52 cards in a deck of cards, and a poker hand consists of 5 of them, the order doesn't matter that you get those 5 cards. 52 choose 5. And again, on your calculator, you should be able to find the choose button. We get 2,598,960 different poker hands. That means it's very, very rare to get exactly the same 5 cards ever again, because there's 2.6 million poker hands. So if we randomly right now take 5 cards out of here, 1, 2, 3, 4, 5. Be prepared to be amazed. What do we have? We have the 6 of diamonds, the 9 of spades, the 2 of spades, the 7 of clubs, and the 9 of clubs. How exciting is this hand as far as poker goes? Not super exciting. We have a pair of 9s. But the chances of getting these exact 5 cards ever again, it's like 1 in 2.6 million. Take a look. You will probably never see this again in your life. But it's not that exciting as poker. So we're also going to today do some counting of poker hands and figure out why is it that some poker hands are worth more than others. Committee questions are typical combinations questions. You have a committee of 2 boys and 3 girls is to be selected from a class of 15 boys and 18 girls. How many ways can this be done? Well, there are 2 decisions. You have to decide which boys and which girls the number of choices for boys is going to be 15, choose 2. And it's a combination because the order won't matter. And for the girls, it will be 18, choose 3. And what do we do with the decisions question every single time? Multiply in between. And you type that into your calculator to get an answer. We'll leave it for now. So if you had 20 students in class, and you wanted to separate them into 3 groups, you'd have 3 decisions to make. We have to choose who's going to be in group A, then choose who's going to be in group B, and finally choose who's going to be in group C. Group A needs 8 students. How many choices would we have? There's 20 students. Choose 8 of them. That 20 choose 8 will give every single possible grouping of 8 kids that exists. Once I've chosen one of them to be my group A, I now need to choose group B. What numbers would I put into group B? Okay, so now the question is, should it be 20 choose 5? Or should it be less? Because you've already chosen 8 students that are in group A. Does it make sense now when you choose group B, there's only 12 kids that are left? And then you choose 5 of them. Now, if you were in that class, and I chose group A, 8, then I chose group B, 5 kids there. Jeremy hasn't been picked yet. He's like, ooh, wonder what group I'm going to be in. What group are you? You're going to be in group C. It's pretty obvious. I mean, if we do the math part of it, you're going to get, there's 7 students left. You need to choose all 7 of them. Basically, there's only one, 7 choose 7 is 1. There's only, like, when you're left, you're going to be in group C. So if you make it all the way to the end, you're going to be in group C. Now, what happens, I'm going to leave a space here for some math, but I'm going to do it again. What happens if you chose your groups in a different order? What happens if you said, I'm going to choose group C first, then choose group A, and leave group B for the end? It should come out to the same number, you'd think, right? But let's look at what, like if I choose C first, there's 20 people, I would choose 7 of them. And then for A, now there would be 13 left, I would choose 8 of them. And now 5 left for parts 5, choose 5. The numbers look different. If you type them into your calculator, it actually comes out to the same. Why does it work out? Well, if we look at the formula, 20 choose 8 is 20 factorial over 8 factorial, 12 factorial. And 12 choose 5 would be 12 factorial over 5 factorial, 7 factorial. Remember that the bottom 2 numbers always add up to the top one. And 7 choose 7, I'm just going to write as 1, because it's not, well, 7 choose 7 is 1, but remember that 7 choose 7 technically would be 7 factorial over 7 factorial. What would the other number be that adds up? 0. And again, we have that 0 factorial, which has to equal 1, is the only way that that formula works. Can you see that 7 factorial divided by 7 factorial would be 1? And so we get 1 that way anyway. And what ends up happening is when I simplify here, notice that the 12 factorials would cancel out, and I would be left with 20 factorial on the top over 8 factorial, 5 factorial, 7 factorial on the bottom. In the black one, if I do the same thing with that, I'd have 20 factorial over 7 factorial, 13 factorial. Then I would have 13 factorial over 8 factorial, 5 factorial, and then this would be 1. And this time the 13 factorials would cancel out, and we would get exactly, and the order doesn't matter, that what I write those numbers on the bottom, exactly the same thing. So interesting that it doesn't matter if you chose group A first, group B first, or group C first. Now, when I simplified the answer, what kind of questions have we done already where you had answers that look like this? Okay? The BBB, the R Mississippi questions, identical objects. So technically, if I wanted to make the same question, 20 people in class, and group A, group B, group C, perhaps I arrange you from youngest to oldest. There's only one arrangement that would happen. You could line up on the wall, youngest person over here, oldest person over there. Then I could spell a word from out of a, and it would be an identical objects question. And every unique word that I spelled up, like if I spelled it above your heads, you'd look up and like, oh, I'm an A, or oh, I'm a B. And every unique word that I wrote above there would make a unique group, 3 groups in total. So this is where permutations, combinations, you could have, I think it's much easier to think of this as a combinations question, but you could have thought of this as an identical objects question as well. So sometimes there are completely different ways of logically solving a question that both work. And unfortunately for this unit, as some of you will discover, there are some ways that you think are logical that are completely wrong. So that happens as well. Okay. Find the number of poker hands with no clubs. If I wanted to guarantee, if I took my deck of cards, and I wanted to guarantee that if I chose 5 cards that I didn't get any clubs, does it make sense that if you took the clubs out, and then picked 5 cards from what's left, guaranteed you wouldn't get any clubs? If you did, something went wrong in the first part. So if I take out the 13 clubs, leaving 39 left, how many poker hands have no clubs would just be 39, choose 5. Which, if we type that into our calculator, is a beautiful looking number. Check this out. Isn't that crazy? Now, you know how I just said that sometimes you're going to come up with a logical thing that you think is perfectly fine that ends up being wrong? What's going to happen on this next question is I am going to solve it in 3 different ways. And each of those 3 different ways, I'm going to become a math salesman. I'm going to try to convince you that that is the right way, makes perfect logical sense. Okay? But I'm not going to tell you, though, It might be, actually, that all three of them do work and are perfectly right. But I might actually lie, and all three don't make any sense whatsoever, and we'll have to figure out the right way to do it afterwards. Or maybe one of them is right and two of them are wrong, or two of them are right, and one of them is wrong. How long has it been on? The whole time, probably. Perfect. Anyways, you'll have to, if you want to rewatch this, the volume's starting now. Otherwise, you have to find an older one. Okay, so here's the salesman. I'm going to sell this to you three different ways. I'm going to make sure that you believe me that all three of them are right. And then afterwards, you have to decide, maybe all three were wrong. Maybe there's something logically wrong in all of them. Or maybe all three are right. Are you ready? We want to find the number of poker hands with at least one club. So what I'm going to do is, in method number 1, what I'm going to do is I'm going to take out all 13 clubs, pretend. All 13 clubs are now in my hand, and I am going to randomly choose one of them. 13 choose 1. I've got 1 club. I now take the other 12 cards, put them back in, shuffle the deck, and I have 51 cards left. I'm going to choose 4 more cards. 51, choose 4. I could get more clubs, but it's possible that I don't get any more clubs. But if I do it this way, my poker hand will have at least 1 club. Method number 2. Just like method number 1, method number 2 is also correct. For method number 2, what I'm going to do is I'm going to use the not strategy. The not strategy makes sense. That's where you go all minus the bad ones, and all the poker hands is 52, choose 5. And the bad ones would be the ones without any clubs. And we just counted 39, choose 5 in the question before as how many had no clubs. And if I take out all the ones that have no clubs, I'm going to be left with at least 1 club. Strategy number 3. I'm going to use cases. For case 1, I'm going to count how many poker hands have exactly 1 club. This is very similar to the method number 1, it's just longer. So if I have 1 club, only 1 club, I'm going to go 13, choose 1, and then from the other 39 cards, choose 4 more. It guarantees that I have 1 club and 4 other cards. Then case 2, and this one's going to be a little long-winded. Case 2, 2 clubs, 13, choose 2, and then other 39 cards, I choose 3 more. Case 3, 3 clubs would be 13, choose 3, and of the other 39, I choose 2 more. Case 4, and I mean, this is long, but it's not hard to do because we're just doing the same thing over and over again. And finally, case 5, all 5 of them are clubs. Should just be 13, choose 5. And because it's a cases question, once I calculate each of those, I would add them up and get my total. First of all, should I stop being Matthew to become a salesman? Were all 3 believable? Excellent. Maybe all 3 are right. Would I do that? Would I not do that? Maybe all 3 are wrong. Would I do that? Would I not do that? Right? I do that. Look at that. No, low level of trust to math teacher ratio here. Like, so, we've got recap. Quick recap. Method 1, take the clubs out, choose one of them to guarantee you have one. Put the clubs back in, 51 cards left. Choose 4 more, guaranteed to have at least one club, might have more. Case 2, not strategy. Count all the poker hands, take away the ones that have no clubs, you'd be left with the hands that have at least one club. And method 3, do it in cases. Case 1 with 1 club and 4 other ones. Case 2, 2 clubs, 3 other ones, so on and so forth. Add up your cases, get the right answer. How many do you feel are right? You feel 2? You feel only 1 is right? 1 is right? 1 is right? 2 are right? Anybody feel like I was actually all 3 are good? No, I must have done some line somewhere. Oh, thanks. All right. You can vote more than once. Yeah, I'll go through each one. If you think that one's right, if your gut says, I like that one, put your hand up. If your gut's like, I'm not sure, maybe, then don't put your hand up. And if you're like, yeah, okay? So, how many people liked number 3? I'll just do a quick, hands up, and then I'll do a quick count. 1, 2, 3, 4, 5, 6 people like number 3. How many people were like, no, I'm a number 3, I don't like number 3? So that means we have people that are maybes. That's their, I don't know. I like it, I don't like it, okay? Number 2, liking number 2. Hands up, feeling confident. 1, 2, 3, 5, 1, 2. Okay, hands up and stay up, because if they keep going up and down, then I don't know. 2, 3, 4, 5, 6. Oh, 10 people are liking number 2. Not liking number 2 at all. 2, 3. 3 are just like, no. Not liking number 2. And number 1, liking number 1. 5 people liking number 1. And not liking number 1 at all. 1, 2, 3, 4, 5, 6. Some of the same people that like number 1 also don't like number 1 at all. Wow! This is fascinating logic. I don't know how that works. I am confident that number 1 is right and wrong at the same time. Okay. Now, if we actually did the math, you would find out that all 3 of them are not the same. So that means that they can't all 3 be right. It could still be that all 3 are wrong, but the answers, here, I'll just write out, I'll quickly for you, write out the answers for some of these. Okay, so here are the answers. The answer to the first one is 3, 2, 4, 8, 700. The answer to the second one is 2023, 203. And the answer to the last one is 2023, 203. So this gives us a couple possibilities. Either the first one's right and the second 2 are wrong. The second 2 are right and the first one is wrong. And it is still a possibility that all 3 are absolutely wrong. Yes.
Well, I think what they mean is
Aren't they calculating? Sorry, say that again. They are.
in the first one, is it like just one club in?
No, because if I, the way that I sold it is I choose 1 club, then I put the other 12 clubs back in, I could get more. Now, when I write out the answers in blue, there is a way for you at this moment to use what we did in previous questions to tell me that you know for sure one of them is wrong.
It's wrong because it's bigger than all of the combination.
Yeah. All the poker hands in total, we figured out was 2.6 million. And apparently, there's over 3 million that have at least one club. What? This is bad. You can't have more poker hands that have at least one club with a restriction than the total number that includes all the ones with at least one club. So we have to figure out what went wrong. These two are right. Now, some things I've heard students say. The students that like the last one, they're like, I knew the last one had to be right because it was so much work, and if there's an easy way to do it, I've learned in math, it's always wrong. It's like, got a bad attitude towards math. That's why I think the last one, because it's so long, works. Okay? But I think the second one is the nicest, using the NOT strategy, right? Taking all of them minus the bad ones, all the poker hands, take out the ones with no clubs, you'd be left with all the hands with at least one club. Okay? That, though, some of you might have felt, no, it can't be that one because that seems too simple. Right? This same bias that you have that math is hard and long-winded and complicated. There is actually a simple answer for this one. But the first one seemed simple and made sense as well. So what went wrong in the first one? Well, if we analyze what we did, okay, I'll do an example. 13 choose one, I could have chosen any club. Let's say I chose the 2 of clubs. Then I put my other 12 cards back in the deck, and now I'm going to choose 4 more. Maybe I choose Ace of Diamonds, King of Hearts, Queen of Diamonds, and 5 of clubs. Now I'm going to count a different one. In the 13 choose one, I choose the 5 of clubs. Put the other 12 cards back in, and now I choose 4 more. When I choose those 4 more, I could have got Ace of Diamonds, King of Hearts, Queen of Diamonds, and 2 of clubs. And that would have counted a different one than the first one. But aren't those hands the same? So, in combinations, when you do, basically when you're doing decisions in combinations, you have to make sure that there's not an overlap in your decisions. So in this example, I could choose the 2 of clubs here, but I also could choose the 2 of clubs there. And in this method, these would be counted as different when they are in fact the same poker hand. How many times did I count things that were the same? Over 1 million times. That's like a lot of mistakes. Right? If I took a half mark, oh, that would be, for every number that you're off by on this unit, I'd take off a half mark. So if you wrote 3 million and the answer was 2 million, I'd have to take off 500,000 marks. That would not be great. That would be very detrimental. But we end up counting way too many. Whereas in the last question, these are clubs, these are not clubs, and so there's no overlap, so you don't create order when you don't want to. That's number one mistake in combinations, is accidentally creating some order when you don't want to. Okay. And with that, I don't know, do you have space on the very end of yours? or take out a different piece of paper, we will look at how to count some poker hands. Okay? We'll do some very basic ones. Okay? And we will follow some basic strategies as we're counting these. And the strategies, when we write them out, will be a little confusing when we just use words, but hopefully will make some more sense once we use examples. Okay? Basic strategy number 1. I'm going to use the word kind to talk about either the same number or the same all jacks, all queens, all kings. We are going to choose kinds first at of the same size at the same time. This is going to be confusing at first, and then we'll see our examples, and then these words will make sense. So we're going to choose kinds, that's either your numbers or jack, queen, king, of the same size at the same time. Then we're going to choose the specific cards of that kind. What does that mean? We're going to start off with an example of getting one pair. An example of getting a poker hand with one pair was what I got at the beginning. I had 2 nines, 9 of clubs, 9 of diamonds, and then 3 other cards that aren't nines, so it could be 2 of hearts, jack of spades, and queen of clubs. This would be an example of getting a pair. It's not a very good hand in poker, but it's better than getting all different. So what do we have to do as our basic strategy? We have to choose kinds of the same size, and in this question, we have a pair. That size is 2. And then we have 3 single cards. So when I go to choose my pair, if I'm counting all the pairs could be pairs of 9s, pairs of 8s, pairs of 7s, pairs of 6s. I would count that by saying 13 choose 1, because there's 13 different kinds in the deck, and I need to choose one of them to be my pair. That's part 1. Choose the kind. Then, after you've chosen the kind, now we have to choose the specific cards. If I chose 9s, it's possible to get 9s, pair of 9s, 9 of clubs, and 9 of diamonds. But it also could be 9 of clubs, 9 of hearts, 9 of diamonds, 9 of hearts, 9 of spades, 9 of hearts, 9 of spades, 9 of diamonds. How many ways could you do that? Choosing the specific cards of that kind, there are 4 9s. We need to choose how many? 2 of them. And this together will count all the different pairs that are possible. Next, I have to choose 3 single cards. I have 12 kinds left. Since these are all the same size, I need to choose them all at the same time. 12, choose 3. That chooses my 2s, jacks, and queens. But I could have chosen jack, 2, and queen. That would be exactly the same. I could have chosen 7, 8s, and 10s. This 12, choose 3 will be all the different ways I can choose 3 other numbers. Then I have to choose which specific 2 for choose 1, which specific jack for choose 1, which specific queen for choose 1. This all together will give me 3 single cards. Which gives us, out of the 2.6 million poker hands, over 1 million different hands have a pair. Given 5 cards, that means you've got roughly a 1 in 2.5 or a 2 in 5 chance of getting a pair. Not bad, pretty good chance. Okay. Now, if we wanted to count 2 pairs, that would be a hand that says, oh, I could still get 2 9s, but I could also have with it 2 10s and 1 other card. That's an example of 2 pairs. In poker, 2 pairs is better than 1 pair. Why is it better than 1 pair? Well, it's supposedly harder to get. Makes sense. To get 2 pairs, you need to already have the 1 pair, plus you have to have the other one as well. If we count this out, and hopefully these strategies start to make sense, can you see that as far as pairs go, you have 2 groups of 2. They're the same size, they need to be chosen at the same time. So when I'm counting 2 pairs, first of all, of the 13 kinds, I need to choose which 2. And the reason they're chosen at the same time is if you choose them separately, then a pair of 9s and a pair of 10s is different than a pair of 10s and a pair of 9s. You're like, no, that's the same. So we choose them at the same time so we don't accidentally overcount and create order when there shouldn't be order in a combinations question. Once I've chosen the 9s and 10s, I need to choose the specific cards. So there are 4 9s, which 2 am I going to pick? There are 4 10s, which 2 am I going to pick? This together counts all the 2 pairs possible. Then I need a single card. Can you see that there are 11 kinds left? Because you can't have another 9, and you can't have another 10. So there would be 11 kinds left. I choose 1. And then there are 4, if I chose aces, there are 4 aces, I choose 1. Now there are some people who would say, couldn't I just do, there's 44 cards left once you take out all the 9s and all the 10s. That takes out 8 cards out of 52, 44 cards left. Couldn't I, for my single card, just do 44, choose 1? Yes. However, if I want to use this strategy all the way through, I'm going to keep the strategy showing up, right? But it's perfectly fine to do 44, choose 1. I couldn't do that in the last question for my single cards. Once I took out my 9s, 4 cards, there's 48 cards left. I can't just do 48, choose 3, because I might get a pair in there. I might get 3 cards that are the same. So that's why in that one I had to do the 12, choose 3. 4 choose 1, 4 choose 1, 4 choose 1. So just to keep the methodology the same all the way through, that's why I wrote it as 11 choose 1, 4 choose 1. Now, we'll do one more. Because I find that between 2 pairs and 3 of a kind, using your brain, it's not always logical to see why is 3 of a kind better than 2 pair. Couldn't 2 pair be harder? You need 4 cards that are right. 3 of a kind, you just need 3 cards that are right. Why is 3 of a kind? Well, let's make it really nice. This is an example. That's a beautiful diamond. This is an example of 3 of a kind. To get 3 of a kind, 13 choose 1. Right? I choose which kind. This is one. These ones are the same size. 13 choose 1, choose my 3 of a kind. Multiplied by, there are 4 aces, I choose 3 of them. Then I need 2 single cards. I choose them both the kinds at the same time. And then 4 choose 1, which king, 4 choose 1, which 5. Choose a specific card. And if I go to my calculator and I calculate the one above to figure out exactly how many there were, 13 choose 2. Okay, this one, 123,552. $54,912. Okay. There are less 3 of a kinds than there are 2 pairs. And compared to a single pair, 2 pairs is significantly better. It's like 5, almost, yeah, even more than that. It's like almost 10 times better. Yeah.